Okay, the next speaker is just me. Okay, let me introduce myself. Now I'm Jinzhu Jia from Peking University. Now I am in Department of Biostatistics, School of Public Health. My research interest includes high dimensional variable selection and causal inference, and also machine learning. Okay, that's it. Today I'm going to talk on the improved covariance adjusted average treatment effect estimate. So let me share my slides. So this is an outline of my talk. First, I will give an introduction about what I'm going to talk. Then I'd like to introduce the general causal effect estimators, and then I'd like to introduce about the covariate adjustment estimators, give some theoretical results, and do comparisons. And in the last part, I'd like to give provide some new methods which will improve the estimator by the variance minimization technique. So I'm considering the Neyman-Rubin model, and this model is also reviewed in the morning by some other speaker. So it is a randomized experiment. Each subject has two potential outcomes here. So for each subject, if he was assigned to the treatment group, then we can only see the potential outcome of YT, and for that subject will also have another potential outcome called YC, but we cannot observe them. And for a subject which is assigned to the control group, we can only see the potential outcome of YC, and for the other potential outcome, it is missing. So here are some notations. We use TI to denote the treatment assignments. It is a binary treatment assignments. TI is equal to 1 means that the subject is assigned to the treatment group. If TI is 0 means that it is assigned to the control group. So if TI is equal to 1, then we denote the potential outcome. The observed value is yi1. If TI is equal to 0, then we denote yi0. So for each subject, we have the observations, yi observation. It is equal to this notation. It means that we can only observe one potential outcome. And in the whole framework, the randomization assignments is the only source of randomness. So the parameter we are interested in is the average treatment effect. It is defined as the individual treatment effect yi1 minus yi0. So for this individual treatment effect, it is not identified because we can only see one of them. But we can calculate the average of them here, and it is equal to the average of the outcome in the treatment group minus the average of the the values if that all of the subjects are assigned to the control group. Also, we see that this parameter is not this parameter cannot be obtained directly from the observations, because for all of the n people, we can only see part of the treatment outcomes and part of the control outcomes. So we can give some estimator. For example, the simple difference in means estimator. It is the average of the outcomes in the treatment group minus the average of the outcomes in the control groups. So by some very weak regulatory condition, we can prove that this top hat is unbiased estimator of the average treatment effect. So this is very simple. This is just the simple Neyman-Rubin model. But we see that this estimator does not use any covariates. And usually when we do experiments, we can collect a few covariates before the assignments. before the treatment assignments. So let's use the X to denote a covariate that is determined before the random assignments. So each Xi may influence or determine the potential outcomes, but the treatment assignments is independent. The treatment assignments are independent of the value of the covariate. So this is a table for the framework. We have a few subjects, and as before, if it is if this subject is assigned to the treatment group, we have outcome YT. If it is assigned to the control group, we have the outcome YC, and only one of them will be observed. But we have some covariates. Sometimes I use ZI to denote the covariates. Okay. So if we have the covariates, can we have a better estimator for the average treatment effect? The answer is yes. A few researchers have analyzed this. For example, the Professor Friedman, he studied the linear regression adjustment of the covariate, the linear regression adjustment for the average treatment effect estimator. So we run regression of the outcome on the covariate. So this is in the treatment group, and this is in the control group. And in the beginning, people will usually use the same slope for the covariate adjustment. So for this model, we call it is multiple. We call it regression adjustment. If you have a few covariate, we call it multiple regression adjustment. So after you use linear regression to adjust the estimator, the question is this estimate is better than the simple difference in means estimator? So Friedman studied this problem and find that it is not always the case that this one will be better. And later in 2013, Lin restarted the Friedman's critique, and he found that if you fit a linear model for treatment group and the control group with different slope, then you have a better estimator. And he proves that this estimator is always better than the simple linear regression adjustment. By simple linear regression adjustment, it means that the slope parameter in both group, in the treatment group and the control group, are the same. And also this regression adjustment is better than the simple difference in means estimator. By better, I mean that the new estimator is a consistent estimator of the true causal effect, and also it has a smaller asymptotical variance. So till now, we see that this is a conclusion about the estimators. The top height is the simple difference in means estimator. It is very easy to understand, and it does not use any covariates. But if we do have covariates, we can use a linear regression model to do adjustments. We can also use another linear model with interaction terms, means that for different group we use different slope, and we see that this estimator with interaction term means that for different group you show different slope. This estimator is always better than the other two estimators. And for a high-dimensional problem, if you have a lot of covariates, that is the number of the covariates is much bigger than the number of observations, then you could use a lasso to first select some covariates and then do the linear regression adjustments using with the interaction term. And the researchers prove that this new estimator is always better than the difference in means estimator that is not using the covariance information. And it is also very interesting that all of these adjustments use linear regression linear regression adjustments. In the adjustment estimator, it does not mean that you have a true model. It said as long as you have the data and as long as it is a randomized experiment, you have the covariate. It does not say that the relationship between the covariate and the outcome is linear. So for this case, even if the linear model is misspecified or it is not a linear model, you can still use the linear regression to the adjustment, and you have a better estimator. So this is a very good result. I think it is very nice and beautiful. My question is that if you do not have a linear model, and say now you have a binary outcome, or other kinds of outcomes like the like some Poisson variable for the count data, and you still use linear regression adjustment, it seems that the model is not perfect, right? So if it is a binary outcome, can we use some other models like logistic regression to do the adjustment? So we did a few research, and we find that if we use a logistic regression model to do the adjustment, we use this kind of model. So this is a logic model, and this model is also studied by Friedman. And if you use this model, then you have to think about the estimator, about the causal effect, average treatment effect. So a good estimator for this one, the average of the treated outcomes can be estimated by this average of probabilities, and the estimator for the outcome in the control group can also be estimated by this probability. So because we are using a logistic regression model, then we can use maximum likelihood estimator to estimate the coefficient beta, and then we estimate the probabilities, and then we estimate the average treatment effect. So this is a procedure. We fit a logistic regression model, and then use a maximum likelihood estimator to estimate the beta, and then we estimate this probability and calculate the average treatment effect using this difference of the average probabilities. So when we do the logistic regression, if for each group in the treatment group and the control group, if we use the same slope parameter, then this is a logistic regression adjustment. And we can also use different slope parameters. We see it is a logistic regression adjustment with the interaction term. This is similar with the linear regression adjustment. Now we guess that for binary outcome, this logistic regression adjustment might be better, but after we do some theoretical proof, we have some good result and also have some disappointing result. The good result is that no matter the model is good specified or it is specified, we always have that the estimate of the average treatment effect using the logistic regression adjustment with interaction or without interaction. Both of the estimators are consistent, and they have the asymptotic normal distribution. So the consistent result has already been studied by Friedman, but the asymptotic normality is the new result in our paper. So after we have the result, we want to do some comparisons. The first comparison is we want to answer the question about if the new adjusted estimator is better than the simple estimator. So we know that the asymptotic result and the consistent result and asymptotic result are both robust. It does not depend on the true model, just like linear model. No matter if the y is linear dependent on x or not, you still, after you use linear regression adjustment, you will always have a better estimator. So for logistic regression, can we still have this result after we do a lot of research and do some simulation? We find that that is not the case. It means that if the logistic model is true, you do have a logistic regression model, then the new estimator using the logistic regression adjustment is more efficient than the linear regression estimator, than the simple difference in means estimator, and it's also it is also more efficient than the linear regression adjustment. So this LR means logistic regression adjustment, okay? And this LRI means that you use the logistic regression adjustment with interactions, means for different groups, you use different slope parameter. So although we have similar result with linear regression estimator, but we see that for the linear regression adjusted estimator, that estimator does not depend on if the true model is linear or not. But here we do require the logistic regression model is right. So this is this is not good, very good, right? Because you never know if there is a true model or not. And this is a counterexample, saying that if the logistic regression model is not right, then our new estimator might be worse than the simple estimator. So now we want to do some improvements, and here I'd like to introduce some alternative estimators for average treatment effect. Now we describe the model using the two equations. First one saying that the yi1 given x means that if the subject is assigned to the treatment group, then it has a mean function called mu1 xi beta, and this mu now it is non-parametric. So we did not specify the parametric form right now, but later we will do specify the parametric form using the GLM. So for the other yi0, it is written, the expectation is written as this one. So this is model specification right now. And to estimate the causal effect, in fact, we are trying to predict the potential outcomes. So for a subject who is assigned to the treatment group, we can see the y1, but we cannot see y0. But if we have the model, if we have the parameter, we can estimate this value, right? And also, even if we see the true result for the outcome, we can also have a predict outcome. So this is the true this is the observed outcome, and this is the missing values. After we have the model, then we can have the predict outcomes for the treated subjects, and also we can predict the outcomes for the controls for each subject if it is assigned to the control group. So after we have this prediction, then we can have a few estimators. The first estimator about the average treatment effect is called the projective estimator. So it is just the difference of the predicted value of y. So in the previous result about logistic regression adjusted model, we used this projective estimator. Another estimator is called the predictive estimator. So for this estimator, we just impute the missing values, and we do not use the predicted value for the observed values. So if that person is observed, then we use the observed values, and if it is missing, then we use the predicted value. So this is called the predictive estimator. And also there is another estimator called the difference estimator. So it is the projection estimator, like what we see here, plus the residuals after you use a projection. So if the model you have a true model, then the mean of the residuals will be 0. So this difference estimator will be the same as a projection estimator. If you have if the residuals are not 0, means that you use a very complicated model and the estimator does not have the property that the sum of the residuals is 0, then this difference estimator can be viewed as a bias calibrated estimator. So we studied this estimator and we find that this estimator is always consistent, and it has asymptotic normative property under field regularity conditions. And this is a very good result, I think, because this result says that no matter if the model is true or not, you always have a consistent estimator about the average treatment effect. And also the estimator is asymptotically normal. And now the question is, how can we estimate this beta head? In the previous result about the logistic regression model, we use the likelihood estimator. But why do we use the maximum likelihood estimator? So by statistical literature, we know that if you have some assumptions on the, if you have the assumptions on the data collection, then if the model is true, the MLG is asymptotically most efficient because it reaches camera raw or low bound. But in a causal inference, as we see that in fact, we do not know if the model is true or not. And we see that even if the model is not right, we still have a consistent estimator about the causal effect, and it has a probability of the asymptotic normality. So now we think we probably want to use another kind of estimator, say the generalized equation, equations estimator. So it is defined on this A as a weighting matrix, and if you choose this A equal to the partial derivative of the mean function with beta, then you have this estimator corresponds to nonlinear least squares. But we do not want to use the nonlinear least squares because now we want to do the minimization of the variance. We want to have a very efficient estimator. So we want to minimize the variance. From the asymptotic result, we see that the variance depends only on the limiting value of this beta hat and also the function of mu. So when you have a function of mu, you can use a maximum likelihood estimator to estimate it, and also you can use this generalized equation estimators. And for generalized equation estimators, we can choose this A such that this after you solve this beta, it gives the minimum. It gives you the minimum value of the asymptotic variance, and this phi beta can be chosen as a gradient of this asymptotic variance. So this, I think, this result is beautiful because the result does not depend on the model specification. Even if the model is misspecified, you still have a consistent estimator about the average treatment effect, and you still have the normality. And by using a very good choice of A, we could minimize asymptotic variance. So finally, I gave a summary. We show that there's tau difference is a consistent matter even if the adjusted model is incorrect. And by some proper methods such as generalized equation model with specified weights, then this estimator has the smallest asymptotic variance. And when the interaction terms are included in the covariate adjustment estimator, the variance of the estimator using GE is always smaller than that without interaction terms. And when the interaction terms are included, we can also prove that this estimator is better than the simple difference in means estimator. And this result is very similar to the linear results. And after careful comparison, we find that a linear result is in fact a special case of our general result. So now we extend the results for linear model adjustment to the generalized linear model adjustment. Okay, this is my talk. Thank you. If you have any questions, I'm very happy to answer here. So let me see if we have questions or not. Yeah, Jiaxin Zhang has a problem.
Hi, thank you for your presentation. That's really impressive. I think I have a really simple or basic question about so the tau difference, is that what you name, tau difference estimator?
Yeah.
I was wondering what are the difference between these methods and the G-Computation methods?
The difference of this method and the G-Computation methods, right? This is the question, right? So I'm not sure what is the definition of the G-Computation method. So I think it is estimator using the generalized equation, generalized estimation equations for nonlinear estimator, right?
Yes, and the G-Computation is like, so you also use the prediction. You predict, so you use covariance and exposure of treatment as a predictors to predict the potential outcome, both in the, so you said you predict two terms. One is that every individual to exposed, another term is that every individual to non-exposed. And you compare the difference between the predicted outcome between those two terms of prediction. And this is the G-Computation work. So
okay, I think for the framework, it is similar to the projective estimator, right?
Yeah, it's quite like that.
And so, also here, the difference estimator at bias calibrated term means that for the observed y, you have a prediction, right? So the difference is residual, right? And then you put the sum of the residual, the mean of the residuals here, and this is a tau difference.
So you are comparing between the observed outcome and the predicted outcome?
Yeah. And you have residual, and you put the sum of the residuals here as a correction for the bias, because it might be misspecified.
Yes, that's right. Yes, thank you so much. Really appreciate it.
Thanks for asking.